Okay, so this is going to be a mini lesson on the origin of the kinematic equations. And reminder, when we're talking about kinematics, we're really talking about like the analysis and the science of motion itself. So just analyzing how particles move. You have 3 kinematic equations given on your equation sheet. I'm going to go ahead and write those the way you see them on your equation sheet. They're going to be Vx equals Vx naught plus AXT. You then also have x equals x naught plus Vx naught t plus 1/2 AX t squared. Let's make that look a little bit better. So our t's and our plus is different. And then the last one that you guys are given on your equation sheet is Vx squared equals Vx naught squared plus 2a delta x. That's how I write it. They write it x minus x naught. So I want you guys to make sure that you can see this is the way that they are given on your equation sheet. I write them a little bit differently, and this is how you'll see me write them as we go on in the school year. And I think the benefit of writing them slightly differently allows for just ease and speed. So the way that you'll see me is V equals V naught plus AT. Delta X equals V naught T plus 1/2 AT squared. And last but not least, V final squared equals V naught squared plus 2a delta x. So these are really just the same equations. I wrote them just slightly differently. There are some benefits to the way that they are on your equation sheet. So I will discuss those really quickly. There are some benefits from that. Let's make this pen the right size. So one of the things you'll notice is that they all use this subscript of x. I should have put one there. They all use this subscript of x as we go along. That's telling you that the kinematic equations only work in one dimension. Whenever we want to try and do anything in 2 dimensions, we'll have to require actually breaking things down into components. And we actually talked about that in the 3rd week of school. We get into the idea of breaking things into components. So that's what that little subscript is saying. So here we're saying the final velocity in the x direction is equal to the initial velocity in the x direction squared plus 2 times the x acceleration times that change in position. So we're saying everything here is x. They could all be y's, they could all be z's, they could be whatever dimension that you want, but they all need to be the same. They all have to be in the same field with each other. One of the other benefits of it, I actually semi-lied. I typically put an F there too. One of the other benefits is instead of using final, they just use X whenever they want you to solve for something. The benefit there is you can solve at any point in motion. It doesn't have to be final. So what I mean by that is if something is in motion from t equals 0 to t equals 12, if you're just using v final, it seems like you have to only do it here. But honestly, if you're doing v of x, it's saying anywhere in this interval you could do it. You could find v of 10. You could find v of 8. At any point, you could find the velocity that you wanted. So that's one of the other benefits of the way that you see them written on your equation sheet. But they're the same thing. Can you tell I'm about to tell you something really, really, really important? One of the most important things that you will ever need to know about your kinematic equations is that the kinematic equations only work with constant or uniform acceleration. So everything that we're about to do is making the assumption that dA dt, or your change in A, is equal to 0. So your A is constant. A great example with that would be gravity. The A is considered 9.81 meters per second squared. Pretty much anything inside our atmosphere, we're going to use the same exact one. It doesn't matter where we are, doesn't matter the mass of the object, it is always 9.81 meters per second squared. That's an example of A being constant. So once again, we can only use our kinematic equations if A is constant. In honors physics or in AP Physics 1, you only ever dealt with a constant acceleration. So this is why these are the only kinematic equations you've actually seen before, is because all you've ever dealt with is A being constant. Put it up here too. Delta A equals 0. But we're in the higher level physics now, and we know that we're dealing with calculus, so we will see some of this. Today, though, we are going to talk about the origin of those original ones. So we're going to create some equations. Can we see this? Yes. The first equation that we are going to create give me a second. There we go. We're going to create the first one, Vx equals Vx naught plus AT. All of these, as we create them, I'm going to make a little side note for a second. We're going to be using the assumption that delta x over delta t equals V average, as well as delta V over delta t equals A average. And then because we're talking about constant acceleration, we're going to say A average is your A because it's not changing. So therefore, delta V over delta T is equal to A of X. So these are going to be our assumptions that we use as we create these equations. So let's come back to creating this equation. It gets pretty easy. The first thing we can say with is, well, the velocity of any point is equal to that initial velocity plus your change in velocity. That's just a basic definition, that anything is equal to your original plus your change gives you your final. Now, we can take this assumption over here and we can say, well, delta V over delta T is just A. So delta V is just A times delta T. We always just use delta T as T. You do need to recognize that anytime you see T in an equation, we're really talking about the change in time. So once again, T really means the change in time in the majority of the equations that we're going to be looking at. So we can say that delta V is equal to A times T. Plug that in, we get Vx equals V naught plus A times T. That's our easy one. But we will now use this one. Now that we have created it, we can use it in our other equations. So we can add it to our assumptions bar. The next one we're going to create is my favorite. One of my favorites, I guess the other two. But delta x equals V naught T plus 1/2 AT squared. We're going to look at this graphically. So the first thing we want to say is we want to go back to that same kind of idea. We're going to start with the idea that delta x is equal to v naught x times t. That comes from the idea that delta x over delta t is equal to our v average. We're kind of reworking that around here. But here, we're making the assumption that v average is equal to v. We're going to look at that if that is constant. If it is constant, we're actually going to look at some graphs here. We're going to have t down here. We're going to have v up here. And we're going to draw this line. I said it was constant, so this is going to be our VOX. Well, as a reminder from the Calculus Boot Camp, if we're going from velocity to position, we're going to do the integral, which is the area under the curve. So if I'm trying to figure out, and notice we have delta x by itself, if I'm trying to figure out delta x, I want to find the area from the curve. So even if we say we're going to make this the t that we're talking about, not t naught, but just the t, whatever t it is, we're going to draw up to that point. We want to know what this area is. Well, this is a rectangle, so area is length times width. The length is t. The width, or the height, well, that's v naught x. So delta x is simply equal to v naught x t. In this situation that we just had, here our a was 0. We know our a is 0 because this line is not changing. Our velocity is the same the entire time. Well, we said we actually wanted our delta a over delta t to be 0. That's really what we want. We don't just want our acceleration itself to be 0. We just want the change of it to be 0. What that would look like is this. I'm going to try drawing that again. Okay, so in this case, let's say that we're stopping here again. We're gonna draw this out again. We're gonna draw up to the point. Well, now I have to find this whole area. This is an irregular shape. And hopefully you remember that irregular shapes, what you want to do is you want to break them up into two regular shapes. So what I can do is I can actually draw a line across here. I promised that was straight. And now I have a rectangle and a triangle. When we know that the area, and notice very specifically a right triangle, you know the area of the rectangle is going to be the length times the width again, and the area of the triangle is going to be 1/2 base times height. Let's start down here. Once again, we're going to see that the length of this is just going to be time, and the height is still going to be VOX. But now to get the total area, we'll label this area, we need to add the area of the triangle. Well, the area of the triangle is going to be 1/2. Once again, the base is going to be time, but then we need to figure out what the height is. Our height is this distance here. So it's going to be Vx minus Vox. So once again, at this point, if we're saying that the area under the curve is our change in x, then we are saying that our change in x is equal to v naught x t plus 1/2 Vx minus Vox t. In order to keep going from here, we're so close, we need to figure this part out though. Vx minus v naught x, well, that's really just delta v. If we go back to our assumptions, we can say that delta v over delta t is equal to a. Remember, we're saying that a is constant, so a average is a. Once again, we're saying that a is constant, so a average is a. Because of that, we'll just move it over. We get delta v equals a delta t. So delta v equals at. I can plug that in. When we plug that in, we get delta x equals v naught xt plus 1/2 at. Once again, that's what's going to go in the parentheses, and don't forget we had this other t here. The last simplification is that delta x equals v naught x. Ooh, that x is way too big. T plus 1/2 at squared. Don't ask me why I put parentheses there. Once again, when we're talking about this term, when we're saying v naught x, we just mean v naught in the x direction. So I'm going to make that very last change so we're not confused about that x in there and say that delta x is simply equal to v naught plus 1/2. Ooh, girl. V naught t, there we go, plus 1/2 at squared. There's our big equation. So once again, that just came from combining the area underneath the curve, and as long as your slope of your velocity line, and the slope of your velocity line is your acceleration, if it's a slope, it's constant acceleration, then finding the area beneath that is just going to be a rectangle and a triangle. So that's all we're saying here is this is the area of the rectangle and this is the area of the triangle. Pretty cool. Now we're going to do the one that's kind of the coolest. It takes the longest to get to. This one is one of the most commonly used equations. For some reason, people forget that this equation exists. I don't know if it wasn't taught well enough in AP1, what the situation is, but this is one of the most commonly forgotten equations. This equation is really cool because there is no t. We can use this equation when we don't know about the time. Notice we do have all the other variables. We have final velocity, initial velocity, acceleration, and your change in position. So we know everything else, but we don't know time. I know a lot of people who will go back and use maybe this equation to find time and then plug it in, and things just get really confusing. So if you are not given time in a problem and you're dealing with kinematics, bam, 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 this is the one that you want to use. So let's figure out how we got here. Well, we actually get here from the equation we were just working with. So we're going to start that one out again. Delta x equals v naught t plus 1/2 at squared. We also need the other equation, the one we had at the very beginning, which is that vx equals v naught plus at. If we're going to solve this, we're trying to get rid of t. So we're just going to do some substitution here. We're going to solve this one for t and then plug it into this equation. So if I solve this one for t, I find out that t is equal to vx minus v naught over a. So that's what we're going to plug in here. Delta x is equal to v naught. Instead of putting t, I'm going to plug this. Once again, plus 1/2 a. Instead of putting t, I'm going to put this. You know what? Let's do this. Drag that down just a little bit for us. T is squared here, so we're going to square it here. In order to show this next part, the textbook I use when I go over this just kind of like skips the math. I know it's the beginning of the school year, so we're trying to put our math brains back on. So I am going to do some of this algebra out the long way for you. Some of you guys might not need me to do this, but some of you guys will be appreciative, I hope. So just to do that, I'm going to go ahead and write this term out a little bit better. We're going to end up with delta x equals v naught, vx minus v naught over a plus a over 2 times vx minus vo over a times vx minus vo over a. When you do this, I want you to notice that we can cancel out an a. In order to get rid of our denominator, which is a huge math skill, it's an amazing math skill to have, we're actually going to take this 2a, we're going to multiply everything by 2a. So we're going to end up with 2a delta x. When I multiply this by 2a, I get 2v naught, and the a's cancel, leaving me with just the vx minus v naught. And when I multiply this by 2a, those cancel, leaving me with just the vx minus v naught squared. I see that I have some things that I can simplify on the side. So over here, so I'm going to say 2a delta x. And then when I simplify this out, I get 2 v naught, I'm going to distribute it, vx minus 2 v naught squared and then plus, well, this is a perfect square, so it ends up Vx squared minus 2 V naught Vx plus V naught squared. So I just FOILed that out really quickly using the pattern of a perfect square. Now I want to see if anything can simplify, so I have 2 V naught x minus 2 V naught x, bye! And then negative 2 V naught squared, and V naught squared is negative 1 V naught squared. So 2a delta x is equal to Vx squared minus V naught squared. So once again, negative 2 and 1 was a negative. And then we can just rework this. We can bring that to that side, give me Vx squared equals V naught squared plus 2a delta x. Bam. So once again, this equation is really cool because there's no time in it, and the reason there is no time in it is that we took the other two kinematic equations that we had, we reworked them for time, and we just used substitution. So remember, substitution is a great skill when you want to get rid of a variable, or when you have equations and you don't know that variable, you can just plug one into the other and get rid of that variable. We will use this a lot. That's a smiley face. It's a creepy smiley face, but it's a smiley face. But just once again, we will use systems of equations all the time. It's just a really good problem-solving skill. The last thing I want to show you is solving for this equation again. Here, we used the graphical definition of integration. But let's see what that looks like when we use the algebra side of integration. So when we use the algebra side, we're going to go back to that equation that Vx equals V naught plus AT. Well, we know that if we want to go from Vx, we know that if we want to go from Vx back to x, we're going to use the integral. So we're going to say that x is equal to the integral of V naught plus AT dt, and that's our variable that's changing. Once we do that, well, we're going to do the opposite power rule. This defined our variable. So we said the opposite power rule is going to say take the exponent, add 1, divide by that. Well, here the exponent on t is 0, so we're just going to add 1. Well, anything divided by 1 is itself. Plus, okay, so now we're going to come here. 1 plus 1 is 2, so it's going to become a t squared, and then we're going to divide by 2, which is the same thing as 1/2. Well, this is starting to look familiar. But, I said when you're integrating without bounds, there's this plus c term. This is your starting amount, your constant. Well, notice I just called it a starting amount. When we're dealing with kinematics and physics, often this is just going to be your initial. So x is equal to this plus c, my initial. How much did I start with? And then we can write the rest of the equation. That is another way of finding them. So once again, your three major equations that we will use throughout this entire unit, throughout this entire year. Your three major equations. 1, Vx is equal to V naught plus AT. 2, delta x equals V naught t plus 1/2 AT squared. And 3, V final squared is equal to V initial squared plus 2a delta x. Get used to using these equations. Be ready to use them later this week.